Okay. So, the formation of total energy. We need to write the total energy of a deformable body. Okay? We need to find the minimum of the total energy to characterize the equilibrium shapes. Okay? Do you believe that this is a modern problem? When the Holy Inquisition did not allow Galileo to study any more dangerous problems, the dangerous problems were the motion of planets around the Sun or vice versa, depending on the field, he was obliged to ask the permission to study a problem. Okay? They allowed him to study the following problem. Take a body in the shape of a cylinder, block this side of the body with a device so that all these points cannot move. Apply a load somewhere here. Problem: find the shape of this body. This is the problem of the deformation of a clamped beam. Okay? Galileo gave all wrong solutions. This is a terrible problem. This problem was solved in a simplified way by Euler, with some simplification, and then it was solved completely, not completely, rather completely by M&M, and in a very complete way by Nastran, which is a software produced by NASA, which uses Cauchy theory of the deformable body. So Nastran plus Cauchy. Euler is assuming that every section remains not deformed. So he is assuming a situation in which the external loads are not deforming the transverse section. In this way, he could find a clever way for finding the solution of this problem. Next step, M&M, using Cauchy theory, found a solution which is good far from the clamped side. What happens here, he could not discover. Of course, engineers are very good. I do not know what is happening close to the clamping region. I can build beams in this way. So this is much more than needed. Okay? But if you need to design the space shuttle, you cannot exaggerate with a lot of strong material placed everywhere where you do not know what is happening. Otherwise, it's very strong. It's so strong that you cannot throw it in orbit. Okay, so heavy is more or less the same problem with airplanes. Okay. So NASA needed to develop, using the Cauchy theory, they developed a code called NASA. So, if people ask you why are you studying complex theories, you could answer that Cauchy invented this theory in 1850, more or less. And NASA was used in 1970 for designing a space shuttle which has been used 20 years later. So if you don't pay Cauchy because his mathematics is too abstract and has not direct applications, you will not have fusion. This is what you have to understand. Our life is short. We are here because our ancestors built for us. If we stop building for fusion, our children will have serious troubles. I know. People want smaller now here and they don't mind about fusion. But, you know, Cauchy, Piola, Lagrange were working for the future. Okay? So, I maybe, as you are having troubles with indices, energies, maybe you know what we do. We start talking about Euler theory, the simplest one. And we calculate the first variation of energy. So we will not have troubles with stress, deformation, integration by parts, indices. You start understanding some important parts of the theory, and then tomorrow we attack another time, the more complicated one. Okay? It is important that you understand the more complicated model, because console gives you the solution. So if you understand the most general theory, you will be able to find shapes of every material you have in mind, every body for nearly every geometry. So this is a tool which is very important. You need to use it. Okay, so let us start with Euler. By the way, in a given moment of our reasoning, Euler stopped and he couldn't move until he received a letter by Lagrange. You have to understand that it was very heavy for a man 45 years old to receive a letter from a young boy 16 years old, sending him the solution of his problem. Okay, so reference configuration of our beam, a straight line. Every section is rigid, so it will not change its shape, and it will remain orthogonal to the main curve. So I described better what I have in mind. You know, you need to be a genius to simplify a problem and getting a predictive model. So the idea of Euler is the following. I have a section. This section has a geometric center, a centroid. Okay? I translate this section in the orthogonal direction and I geometrically build a cylinder. The centroid is spanning a curve. If you are moving this in the correct way, orthogonally to the plane of the section, you get a straight line. Okay? This straight line is drawn here, and it is the mean curve. Okay? We assume that when the mean curve has a shape, every section remains orthogonal to the mean curve. So the section which was orthogonal here will remain orthogonal even if the mean curve has changed its shape. Okay? So I have said this with words. Now I write it with formulas. How am I doing it? The beam is long L. I choose a curvilinear abscissa S in the reference configuration, and I label every section with the label S, small s. Then I consider the vector R of S which is the displacement U of S, R of S. U of S is the displacement which is transporting the centroid in the reference configuration to the centroid in the actual configuration. So, if this is the vector E1, and this is the vector E2, we don't talk about E3 because we assume that the motion is plane, just for beginning. Okay? If the origin is here, then the position of the centroid is given by S E1 plus US. This is equal R of S. So the parametric representation of the curve actual shape of the mean curve is given by this equation. Okay? So in a sense we are describing the kinematics of our being. If I give you U of S, then you know the shape of your body. Okay? Why this model is very simple and very useful? Because you have only one variable, one real variable for level points, all material points of a given section. You don't need to follow the section, every point of the section. Why? Because you know when it is decentroid. When you have built all the points of the curve, mean curve, in the actual configuration, this section is orthogonal. So geometrically, you know how all the points of every section are placed. So you have, in a sense, what we can call a reduced kinematics. Instead of being obliged to follow every point in your cylinder, to say that the shape of the cylinder is maybe this one. Okay, so this point is here, this point is here, this point is there. So instead of giving the function k of capital X equal small x, which is the complete kinematics in a three-dimensional continuum, if you assume that every section is always keeping its own shape, you can reconstruct the actual shape of your body simply knowing where the points of the mean curve are placed. Okay? So this is what we can call a reduced kinematics. So knowing where the points which are centroids of your sections are placed, only knowing this, you know the complete shape of your body. Okay? The interest in this reduced kinematics is clear. You have only one real variable, S, instead of 3 capital X. Okay? For understanding this, you need to be a genius. Euler decided to use the reduced kinematics. Okay? However, he didn't manage to find the minimum of energy. He wrote the energy, but he didn't manage to find the minimum. Lagrange managed to find the minimum. Okay, so for joking a little bit, I can tell you when you have a problem, you need an Italian for solving it. Okay? I put your leg because I know that Polish people are very nationalistic. At least the other generations. I don't know, maybe the younger generation are not. Okay. So now we have to write the deformation energy of an Euler beam. Okay? We are clever and we follow Euler in another simplification. This U, which can be decomposed in one component along E1 and in another component along E2. Okay. This U, we assume it is only a transverse displacement. So we assume that this vector has no component along E1. Okay? So the standard theory of real functions of a real variable can be used. what is the shape of your beam? The graph of the function u, or the component of u in the E2 direction. Okay, so we call this, a mathematician will be very upset, because now I will call with the same letter the field, the component u. So here maybe we could write an arrow at the top for telling that this animal has two components, u E2 plus w E1. Okay? W is 0. So you have only transverse displacement. So if you have the interval AB, you write the plot of this scalar function, you draw the plot, and you have the shape of your beam. Okay? Imagine that you want to discover the direction of one section. Euler knew very well that the derivative of the function u of s, so du over ds, is giving to you the tangent of this angle, where this is the tangent straight line to the graph of the curve. I hope that you are familiar with it. Yeah? So you know that if this is phi, the u over ds is tangent to phi. Actually, tangent phi has been invented talking about tangent curves, tangent straight lines to a curve. Okay? So, if you want to know the angle of rotation of a section when you are passing from the reference configuration to the actual configuration, you calculate the derivative of us. This derivative is the tangent of phi. You calculate arc tangent of du over ds and you find phi. Okay? So when you know the displacement us, you know every rotation of every section, okay, and you know the shape of the mean curve. So you know everything about your beam. When you have a difficult problem, you should find a clever simplification. Euler knew that Galileo had failed in solving the problem of the deformation of a beam, and Galileo was not stupid. So instead of attacking the most general and difficult problem, he found a clever simplification. Unfortunately, we cannot teach you how to simplify a problem for getting a meaningful problem. Okay? This means to be creative. Okay? Okay. Now, we are very close to write the deformation energy in the case of a planar Euler beam without axial displacement and only a transverse displacement. If you have a beam, a cylinder having this shape in the reference configuration, and then you deform it in this way, you have a deformation energy related to bending. How can I measure the bending of this small piece of beam? I consider phi of S. Phi of S plus ds. So two closed sections, and I consider the rotation of each of these two sections. Then I calculate phi s plus ds minus phi s. I divide this times ds, and I find the change of relative rotation of the sections per unit length. Okay, so this is the bending deformation of our beam. Okay, ds is small, this is the derivative, this is phi prime. Okay? Okay, I will need this picture later. So, imagine to have a generalized spring. Instead of having the spring, which is deformed because of elongation, you have a spring which is deformed for bending. It is a good conjecture to say that the deformation energy is 1 bending stiffness Kn phi prime squared. Okay. Now you could stop me and you could tell me, but how do you know this? From which hat you are taking this rabbit out? Kn is a constant which we can call bending stiffness. Okay? I do not have any answer except one. At the end of all this theory, I will get some results which forecast the shape of a beam. If I go there and I measure the shape of a true beam, I compare it with the forecast shape of that beam, and I find a result which is reasonably equal. Then I will say magic. My theory works. I remember that when my professor of rational mechanics came to us talking about the motion of planets, he said the magic power of science became clear when people measured a change in the forecast trajectory of the external planets of solar system, and instead of saying that the equation of Newton went wrong, conjectured the existence of another planet whose presence was disturbing the orbits of the internal planet. They wrote the equation. They calculate the mass and the trajectory of the assumed planet which had not been observed before. Then they used the telescope and found it. This is the power of science. You can predict the behavior of system which you never observed before.
Francesco, why do you want to avoid saying that this is work done by internal forces?
What?
That's what you wrote.
No, I want to call it deformation energy. Because this is what Euler was doing.
Okay.
I want to be faithful. Why? Because you are beginners. Okay? If this idea came to Euler in this way, most likely this is the simplest way. So we will elaborate on it later. Okay? So Euler started a sequence of conjectures. Sections are rigid. Deformation energy for bending is given by this formula. Then we will see. He did some calculations, and at the end of these calculations, he could forecast what happens to a beam. You clamp one beam on one side, you load it with a load, this is the shape of the beam. Then you go, you measure. If your measurement is reasonably close to your theoretical prevision, then your theory is good. Okay? Most likely, this is the Epicurean philosophy of science. Of course, you can say that as I am Neapolitan, and thus Napoli is the new town in Greek, a colony of Greece. Of course, I want to say that everything has been done by Greeks. Okay? But be sure that this was clearly understood by us. So we close the philosophical parenthesis, okay? And we conjecture this. So I cannot give you any reason except the results which we will get at the end of the story. So you must trust Euler, my reading of Euler, the tradition which is transmitting us these results. This is very difficult. You must trust. This is the big difficulty in teaching mathematical physics. Okay? Okay. Now Euler started doing calculations, because look, you can calculate the derivative of this. You have the derivative of the tangent times phi prime, and then painfully you can write the energy in terms of U. Okay? But this complex reasoning in this moment is not needed. It is feasible, but it is not needed. Why? Because we can assume that this beam is deformed a little bit. So, tangent of phi, which is equal sinus phi over cosinus phi, is nearly equal when phi is tending to 0. This is nearly equal to phi. Okay, this is a Taylor expansion. Check that the Taylor expansion of tangent phi in the neighborhood of phi equals 0 has as a first term phi. Okay? So this is true when this angle is small. So you have a small deformation of your beam. We can do it. You know why the beams, metallic beams in civil buildings, are deforming 10 to the minus 5? Because engineers want to be sure that this approximation is true. There is no other reason. Okay? So, tangent phi nearly equal to phi. So, du over ds equals phi. So the deformation energy is 1/2 km u second squared. Okay? Now, do you remember that I told you that the deformation energy in the idea of Cauchy depends only on the first gradient of displacement? While Piola said, what are you doing? You need higher gradients. Okay? Piola wrote in his book, look, our father ordered. He used a second gradient energy. Who told you that in continuum mechanics first gradient energies are good? No, the big problem, the big difference between the Italian Lagrangia and the Italian Piola is that Lagrangia changed his name in Lagrange and wrote the name in French. So he was hurt. While Piola was so nationalistic that he kept writing in Italian. Okay? Okay, now all philosophy is ended. We need to do some calculation. So, our beam is clamped in one side, and let us imagine that it has some applied force, a force per unit line applied along its length. Okay? Okay, I hope that you know that potential energy of a constant force is force times displacement. You remember, mgh, I think. Mg is the gravitational force, and h is the displacement from along the vertical from a given point. Okay? So you could be upset if I explain you this. Okay? I don't know why students are never upset if you explain you something more. Okay? You must be upset. I know this why. You are daring to tell me something which I know already. Okay? So, total energy equal integral between 0 and L of B, the force per unit line, times U of S, ds. We assume that B is a function of S. You can have a different force in different modes. Okay? By the way, I'm using the word force. D'Alembert and Lagrange wrote that there is nothing more obscure than the concept of force, which should be carefully avoided by any healthy person. So I could tell you the external world is exerting an action on your being, and the potential energy of this interaction is given by this. And we never pronounce the word force. Okay? Plus integral between 0 and L of 1/2 km u second squared ds. Okay, I tried to help you telling this the force applied per unit line. Bs times ds is the force applied to this element ds. However, answering you in this way means that I am against the philosophy of Lagrange. I tell you this. You take this being, you consider it with a given shape, okay, and simply because this animal moved from here to there, it has a potential energy, which is given by Bs us ds. So I have this body. If it is here, it has a potential energy. If it is here, it has a long energy. So I am integrating along the whole interval 0L all the elementary potential energy. Okay? Now, the twisted people call BSDS a force. Okay? But we are healthy and we talk about energy, simply energy. Okay? So, do you agree that this is a total energy? We don't have any other kind of energy. Either bending energy or positional energy. This is a very good model for a beam which is ground. Okay? Now, which is the shape of this beam in equilibrium? Find the minimum. Okay? The recipe is the following. When you have total energy of a system, for finding its equilibrium configurations, you need to find the minimum of the energy. So we were clever enough to describe the kinematics. we were clever enough to describe, to find, not to find, to conjecture total a shape for total energy. Now we are facing a technical problem. How to find the minimum of energy. Okay? Euler arrived up to here. And he stopped there. Because this is a difficult problem. Okay, the few girls present here will be happy to know that this problem has the name of a pin. This is the famous Didot problem. You know, when you have optimization, you need to ask help to a woman, usually. To find the best way for doing something, ask the advice to a woman. Okay, do you know the story of Didot? She arrived in the location of where Carthago were bound to be founded. The king of Numidia said, I will give you only the land which you can cover with with the skin of coal. Okay, you know the piece of dried skin that you take out for building, for constructing bags, you know, clothes. I don't know why now in this moment I have the quiver. Okay, anyway, what she did, she cut this skin in very narrow stripes. She built a very long cord. Then, given a perimeter, she knew that the maximum area is a circle. And with this small stripe, she could get enough land for building a city. Now, where is the mathematical problem? Given a perimeter, find the curve, the closed curve, having maximum area. This is the Didot problem. This is the prototype of the problem of calculus of variations. What is the unknown mathematical object here? A function. The unknown mathematical object which we must find is a function. In the Didot problem, you have a curve which is given by a function. In this problem, you have the shape of the beam, which is a function. We have lost the books of Greeks, so we do not know how Greeks could prove that the curve having maximum area with a given perimeter was a circle. The modern theorem has been proven by Lagrange. So now we must find the minimum of this energy using the technique developed by Lagrange. Okay? So if you feel too young, I repeat to you, you are much older than Lagrange when he solved this problem. So you can imagine I am a scenario person. Okay, so this is the energy. This is the energy. You remember what we said this morning? How did we prove that the derivative of a function is 0 in the maximum or minimum? The first variation of this function has to be 0. Now you have to be very careful, because here we do not have a function. We have a functional. What is a function? It's a method which takes a function and produces a number. So the domain of our function is a set of functions. Okay? This is the delicate point, and this was the crucial block in the mind of Euler. So you needed a young brain who was not blocked by previous knowledge. Okay? So you understand now why we need young brains. Okay? If we destroy our young brains, we will be lost. So I write the variation of total energy. So what I do? I consider one shape. I consider another shape which is obtained by the previous one, adding a small disturbance. And I try to estimate the difference between the total energy in U plus delta U minus the total energy in U. Look, this is a path notation. I am lazy. Maybe it is better if at least one time I write it in this way. I want to say that you must consider the whole function. So this dot here is reminding you that you need to consider the whole function, not the value in one point. Okay? Minus E T U dot. Okay? Now, ET is here. So, integral B of S US plus delta US ds minus integral BS US ds plus integral 1/2 Kn U plus delta U second minus integral 1/2 Kn U second
Square.
Square. Okay. This is ET U plus delta U minus ET U. Okay. The integral of the sum is the sum of integrals. So, this goes away, and we are left only with this term. This is the simple story. Then we have a more complicated story. So, I write plus integral Okay, the derivative is linear. Okay, so this is u second plus delta u second. Then you develop the squares. So you have 1/2 kn u second squared plus delta u second squared plus 2 u second delta u second. Minus this end. Okay? Okay, this goes away with that.
Wszystko wiecie? Wiecie czy nie?
Too quickly. You agree? You agree? Minus integral 1/2 kn u second squared. And here was u second squared. Okay? You agree? Huh? Can I go ahead? So, this goes away with that. You have this bracket. Delta u second squared is an infinitesimal of higher order. It is the square of something very small. It is a remainder. Okay? So, the first variation, delta et, is equal to integral bs delta us plus kn u second delta u second ds. Remark the beautiful property of this equation. This is a linear function of delta u. So this is the generalization of the Taylor expansion truncated at the first order we have used for proving the criterion of zero derivative when you have a maximum or minimum. However, our story is not yet ended. When you vary delta us, you vary also its second derivative. This is us. Zero. Yes. Yeah. Zero. Okay. So let us go back. We have US, and then you have US plus delta US. Okay. This delta US is arbitrary, and you change delta US everywhere in your interval. So when you consider a delta US, its second derivative is given. You cannot change independently delta US and delta US second. This is a technical difficulty, because we need an expression in which only delta US is applied. Okay, we can integrate by parts. So let us focus on this term only. K M U second delta U prime is equal to Km U second prime delta U prime plus Km U second delta U second. This is obvious. Leibniz rule. Okay? So I can write minus equal. Okay? Then I can replace here this element. Okay? Now I want to tell you for nowadays, these are trivial properties of functions. But when Lagrange was doing this, there were very few books in which these properties of derivatives were shown. It was really at the border, at the boundary of knowledge. So, instead of this animal, I can write Km U second delta U prime minus Km U second prime delta U prime. Okay? You can say, but did we improve our situation? Yes, we did. Because delta ET equal the integral of the derivative we know how to calculate. Is the function estimated at the extrema of the integral. So this integral is equal to Km U second delta U prime between 0 and n. We got rid of this. I mean, this is not zero. We have the expression of this. Then this animal here is always the same, and we leave it without changes. And then we have minus E integral 0 L of Kn u second prime delta u prime. Okay? We assume we integrate by parts and order. So Km u second prime delta u prime is equal to Km u second delta u plus Km u second prime delta u. This is the value we have here. Okay? Somebody said that I wanted a lab because I wanted a blackboard with moving sheets. I don't know why in these times people are giving their talks with slides. Okay? If you are not able to give your talk on the blackboard, you have not understood what you are telling. I know it is challenging. One day I will not be able to do this. Then I will ask to be pensioned to retire. Okay. What we have to do now? We have to replace that term we have calculated. So delta ET equal Km u second delta u prime 0 L plus integral 0 L ds delta u L. Instead of minus this anymore, we write minus integral of Kn u second prime delta u prime, okay, and then plus integral 0 L Kn u second delta u. Okay? Now, the integral
minus over there.
Yes.
And there plus and over minus.
Okay. Minus okay, so plus equal, so minus Kn u second prime delta u. Okay, should work. Okay. Every integration by parts, you get a minus. With two integration by parts, you get plus. This is a trick. I think this is the 20th time I'm doing this calculation on a blackboard. So at the end, you know the tricks. But anyway, you must check everything. Every integration by parts you have a minus. Okay.
And every integration is from 0 to...
Integration is 0. Okay. Now, the integral of the derivative is equal to 0. The value of the function is 0. Okay? Now, do you know how we need to proceed? We need another theorem. Bet who is the inventor of this theorem, Lagrange. I have an interval, 0 and I have a function defined in this interval. We call it f of s. Then we know that integral between 0 and L of fs times an arbitrary function delta us is always equal to 0. What can happen to your function f of s? Theorem of Lagrange. The poor function f can be only 0. The theorem is clear. I give you the hint of the idea of the proof, which is very easy. You choose for delta s a function like this. You do it very, very narrow and very, very high. You apply here the theorem of the mean of an integral. So, imagine that this is large epsilon and this is high h. Okay? So, outside the interval large epsilon, delta is 0. Okay? So, this is integral between minus epsilon over 2 plus x0 and x0 plus epsilon over 2 of fs delta us. Okay? So, the theorem of the average for an integral tells you that this is equal to the length of the interval of integration, which is epsilon, times what? The average value of the integrand function. Sorry, not the average. The value of the integrand function in one point inside the integrand. So why you are doing this face? You worry me. You know, I always thinking that I'm not telling something correct. If you have one function in one interval, the integral of this function is what? The value of the function in one point times the length of the integral. So this area is the area of this rectangle is equal to the area of the lower part under the graph of the function. So this is the theorem of equivalence of a rectangle to the area of a region under the graph of the function. This area is equal to the area of this rectangle, where this height is the value of the function in one point. Of course, you need to assume that the function is continuous, otherwise this is not true. Okay? This is calculus, first year. Okay? I apply this to this integral. The interval is long epsilon. I have f of x bar, delta u of x bar. Okay? X bar is a point here, somewhere. Okay? Then, when epsilon tends to 0, f of x bar is tending to f of x0. If I was clever and I choose h equal to 1 over epsilon, epsilon times something which tends to 1 over epsilon tends to 1. We have proven that f of x0 equals 0. Okay? So, if delta epsilon t is equal to 0 for every delta u, the function which is inside the integral multiplying delta u has to be 0. Okay? Somebody could tell me about what you are doing in 0 and L. This function here is 0 together with all its derivatives in 0 and L. So this animal and this animal are 0 for the moment. Okay? If you have to say something, tell it now. Okay? Again, boys and girls, this reasoning is Lagrange. In high school, it is. Okay? So, delta epsilon t equals 0 implies that Bs plus Kn u second equal 0. This is a necessary condition for equilibrium of a beam. You know, I must try to twist you very well, because you must become variational, intrinsically variational. Okay? So now we stop for a while and we discuss a little bit. This is a differential equation. We have 4 derivatives to calculate. Okay? So, if you know the primitive of B, you get Km second prime. If you know the primitive of B, you get Km yourself. Then you divide everything times Km. Okay? You calculate 2 times again the primitives, you get U. So, how many constants of integrations do you need? 4. 1 for every integration. Okay? How do you get these integration constants? What? The beauty of variational principles is that they answer to all your questions. Sorry? So you have that U of S depends on 4 new variables, and you must find the value of these 4 variables. No, they are constants. You need 4 constants of integration. I can try to do some quick calculations with an example, but I don't want to do it because you must reason. Then we do an exercise. Okay? Mathematics is not giving you every answer. Again, which is the question? Okay? You must ask the question. Okay? So now I hope that the woman present will forgive me. Life is choosing among accessible states. Usually women want something which is not accessible. Okay? Life is a set of choice under the constraint of being physical. Okay? So, you want the minimum of energy among the accessible states.
We call it kinematical ability.
Yeah, you can call it, but I don't like it. No. So, for instance, I told you that I want to study the equilibrium position of a beam which is clamped on the left. Okay? So, U0 must be 0. Okay? Imagine that you have nothing here. You take this beam and you lower it, and it has less energy. You lower it, it has less energy. You can go to minus infinity, you have less and less energy. There is no minimum. You must block with a clamp this beam. Okay? Blocking with a clamp the beam means that U0 is equal to 0 and UL is U prime 0 is equal to 0, because the tangent here has to be horizontal, because you are not blocking the centroid. You are telling also that the section cannot rotate. So U prime is 0. So you have specified the kinematical conditions. Okay? So delta U prime 0 is 0. You cannot do anything to vary it. And delta U in 0 is again 0. So you have only this. Now, if you are twisted and you want to talk about forces, you can suffer a lot. Invent physical intuition, talk about crazy and absolutely useless concepts, or you can ask to the energy to be the minimum. Okay? I do not know where the free end is placed. So I must try all positions for the free end. So I must change delta U arbitrarily, keeping the tangent horizontal. So I look among accessible states. This is an accessible state. This is another accessible state. I can change the position of the ending point in every way which I like. Delta U is arbitrary. Delta U prime is 0. Therefore, this animal has to be 0. What it means, I do not know. I do not want to know. I refuse to know. This is the condition coming out, the requirement of minimum of energy. Period. If you want that your shape is minimum for energy, then you must accept that minus Kn U second first equal in energy. Okay? Then this animal is 0. So we have killed this, we have killed this plus that, we have only this animal. Now, assume that you have chosen the value of the position of the ending point. I can rotate the section here in the way which I like. I change this angle and I get another admissible shape. So del phi prime is arbitrary. So this is 0. And I add the condition Kn U segment L in an equals. So I fix the kinematical conditions. So I tell something which this system cannot do. I cannot change the position in 0 and I cannot change the angle of the section in 0. Then I vary everything. I get a differential equation and I get exactly the number of boundary conditions which I need. Because 1, 2, 3, 4, exactly 4 boundary conditions, which I need for finding the 4 constants of integration. When I go to a conference and I talk about variational principles, there is always somebody who raises his finger and says, how do you do with boundary conditions? And I say, so, this is the last problem when you have variational principles. Variational principles produce to you the exact number of boundary conditions. So I think that you must know it immediately when you are a child. Maybe we should send you a message when you are 6 years old. Okay. Using variational principles, the boundary conditions are given automatically. You will not understand what people are telling to you, but you learn by heart. Okay? Okay. This is the prototype of a mechanical theory. So before stopping, I want to list you the steps. Step number 1, find the kinematics of your system. Okay? D'Alembert said, la cinématique d'abord. You start with the cinematic. Why? Of course, every woman wants to be as rich as possible. Okay? But we have a budget constraint. We cannot give her more than what we earn. Okay? So there are admissible states. So you must fix at the beginning the set of configurations which are accessible. Then you look for the minimum of the energy among accessible states. Okay? I know it is obvious. You know, the fact that you consider obvious is the evidence that we have twisting it. You will be variational for all your life, and this is very good. Okay? So, once you have chosen the set of admissible states, you start doing your calculations. to find necessary and sufficient conditions for being a minimum. Okay? We integrate by parts, and following Euler, we find this differential equation plus 1, 2, 3, 4 boundary. I have, my dear friends, a very bad news for you. If the function u is derivable 4 times being minimum is equivalent to verify this condition. But new. There are functions which are 2 times derivable only, and they are the minimum of energy. This is a very bad news. People are calling this strong conditions of minimality, or strong condition of stationarity, for including maximum and minimum. So, among functions which are suitably regular, these are good for finding the equilibrium shapes. But if the function is not regular enough, this technique is not applicable. Okay, now we are tired. I have said you this bad news, but I tell you also that a Soviet mathematician whose name was Sobolev understood that all this integration by parts is absolutely useless. In the sense that if you want to write a code for solving a problem of minima, this integration by parts is useful because you get the correct boundary conditions. However, the condition of minimality has to be attacked in a different way. So Lagrange was rather right in many aspects, but he, luckily for us, he didn't solve all problems.